So we've been wrestling with this problem of how do we establish causality, and we talked in our last session about two different sort of broad philosophical approaches for being able to demonstrate causality, one of which is experimental designs, which we'll talk about a little bit more today. So as you may recall, that conversation about causality put forward the argument that in order to make a causal claim, we need to be able to demonstrate four things. We need four things to be in place, right? So one, cause should precede effect, that we think we live in a world where time order matters. And so we should be able to document that that is in place. We should be able to identify an association, a relationship between two variables, whether that's a difference between groups or a correlation or some kind of pattern that we can point to say, here's evidence that X is causing Y. We need a story that we can tell, a causal mechanism behind that. And the tricky one, the one that really causes research methodologists to scratch their head, is how do we establish non-spuriousness, which is a fancy way of saying, how do we show that we've identified the correct causal relationship and it's not something else that's driving that pattern, that we've ruled out those other possibilities. So to be able to make a claim that we've effectively ruled out those alternate cause possibilities, we can use experimental designs, and particularly true experiments are very good at doing this. In fact, I don't want to say there's no better strategy, but it's probably one of the strongest strategies we have for being able to rule out alternative possibilities. And we'll talk more about why this works so well, but really the critical piece in all of this is the ability to randomly assign individuals or whatever we're studying into two distinct groups, one group a treatment group and one group a control group. And the ability to randomly assign to groups means that we can take advantage of the fact that random processes basically distribute things and people and cases in a way that's more or less even. Occasionally you'll get too many women and not enough men in one group and vice versa, but those differences are usually pretty small. And it's unlikely that we're going to see big, meaningful differences between groups. And this is true across a whole range of things, right? Things that we can, measure or record, like the age of people, but also across things that we can't really measure or record. If people have an undiagnosed underlying heart condition, right? A random process will put those people into a treatment and control group with roughly the same proportion. And so it's a way of essentially creating that scenario that we talked about in our last discussion of ceteris paribus, that all things are equal, and we can be able to make the claim that there's not something else driving this, that the only thing different between these two groups is the treatment. And so any difference in the outcome is something that we can attribute to that treatment with a credible causal claim. Ideally, the researcher is able to control the setup and design of this experiment in such a way that prevents contamination or prevents sort of other factors being introduced into that process that might muddy the waters. And if you can do a true experiment, this is really effective. The problem is that in many of the social sciences, we don't actually have the power to do random assignment of individuals to groups. Does that mean that an experimental design is not useful? No, it just means that a lot of times when we use an experimental design or an experimental logic, we're doing something a little bit different, something that is helpful, but maybe not as solid in terms of establishing non-spuriousness. And so one of the ways that this could work is could be a quasi-experiment, which is something that kind of looks like an experiment, but because we're not responsible for randomizing groups, it's a little bit harder to make the claim that we've essentially controlled for all the potential factors. So this could happen a couple ways. It could be that you have a policy that you're testing or an intervention that you're testing, and people get to opt in to different programs, right? So the example I oftentimes use is I could be running two after-school programs, one that plays dodgeball and one that does extra tutoring. And parents have a choice which of these programs that they sign their kids up for. And I could look at that and say, well, I didn't randomly assign people to these groups, but roughly the same proportion of parents signed up for both groups. I'm looking at the ages of the kids, they seem roughly the same. I could eyeball it and say, these groups look roughly the same, right? Same proportion of boys and girls in the classes. It's basically a random process, or it has produced a process where the groups are equivalent. I shouldn't say it's a random process. It's not a random process. People opted in. But the problem with that is that there may be unobserved differences between parents who sign their children up for dodgeball versus extra tutoring, and that those unanticipated differences or those uncontrolled differences might affect how a child does in dodgeball or how a child does in their schoolwork, in a way that could bias my results or could contaminate my results, or just make it so that I can't really make a claim that I've ruled out those alternate possibilities, because I haven't, because there's potentially those differences between groups. Sometimes nature or the world or human beings will distribute cases in a way that looks kind of random. And so I was at a conference a couple years ago, and an individual was making a case about the Serbian army's ethnic cleansing campaign against Albanians in Kosovo during the 1999 Kosovo War. And the claim was that there was an area in the south of Kosovo, and the Serb military had a choice to drive Albanians being ethnically cleansed to either like Bulgaria or to Albania. But the difference was essentially negligible. It was the same distance either way. And so this person was making the case that these Serb soldiers were essentially mentally tossing a coin, and some folks were being sent to Albania and some folks were being sent to other countries. And that was basically a random process, right? And so then you've got this sort of natural experiment, the situation in which nature or ethnically cleansing Serb soldiers are putting people into different environments, more or less by random. And therefore, if we see differences between those groups, we can attribute it to that different environment that they were placed in. And maybe that's a useful thing to do. And when nature sort of hands you these kind of random assignments, that can be a powerful, powerful research design. Okay, so other ways that we can handle situations where we don't have sort of perfect control over randomness, we could try a matching strategy. So instead of looking at my treatment group and my control group and sort of looking at differences between the groups, I'm going to sort of move away from the groups because the groups are not equivalent, because I wasn't able to randomize things, because people self-selected in, because of a whole host of reasons. And so instead, I'm going to identify individuals in the control group and the treatment group and try to match individuals that are similar. So in my control group, I've got a man 35 to 40 from Minnesota. And I'm going to look into my treatment group and try to find somebody who's similar, a man 35 to 40 from Minnesota. And so I'm matching those two individuals up, and I'm saying, okay, if there's a difference between the control and the treatment group, then maybe I can attribute that to the treatment. This is essentially the comparative design logic, and we'll talk more about that later, with the comparative method. It can work, and if you are able to control a great number of things, it can work fairly effectively. This is the testing logic that was described by the folks at High Plains Fair Housing for how they demonstrate discrimination by creating sort of matched pairs, people who are sort of similar on all these different dimensions, to see if they're treated differently. There's been attempts to sort of scale this up with data sets where you can essentially treat a observational data set as if it was generated through some sort of experimental process with treatments and controls. At the end of the day, it runs into the exact same problem that all non-experimental designs and non-random assignment designs run into, which is you can only check so many things. You can only look for so many things and make those comparisons and say these cases or these individuals are similar or identical. There's always stuff that we can't anticipate. There's always stuff that we can't observe. And as a result, there's not going to be the ability to say we have confidently ruled out all the possible alternatives that could explain this pattern. So matching can work, and in some situations, maybe that makes a lot of sense. In other situations, we sort of throw away the whole treatment and control group comparison and say, I'm not going to do that. I'm not going to waste my time making those comparisons across treatment and control groups because those groups are too different anyway. And so if I have my treatment group and I'm looking for something to compare that treatment group against, the best thing to compare the treatment group against is that exact same group at a previous point in time, ideally before the treatment. And so a before and after test sort of looks at your treatment group before you apply the treatment, your treatment group after you apply the treatment. And if you see a difference, we just attribute that to the treatment. And that can work pretty well. In fact, that's great if you're dealing with something over a very short period of time. If you're doing a study that's going to last a couple different years, that might be difficult to sort of draw credible conclusions about non-spuriousness, because what can happen in that intervening time is all sorts of things can sort of go wrong, right? There could be a massive recession that changes people's behavior. There could be a pandemic that changes people's behavior. There's lots of things that could happen that could sort of set things on a different course that you would have to sort of work around or isolate. And over a long time period, that before and after test is going to get muddied. If you have a control group, that can help to sort of balance out those time factors, things that can pop up between your first test and your second test, because whatever happened, pandemic, recession, war, whatever disruptive thing sort of plays out across society, it's going to be playing out in a way that's going to affect your control group and your treatment group in theory in the same way. And so they remain similarly affected, and they remain a useful point of comparison when you have the treatment control group. So you can actually do a before and after test alongside or in conjunction with a typical experimental design. I will flag that not every situation makes sense for a before and after test. And so maybe I'll pivot here and talk about this question about when to test groups. If you're able to test before and after, that's generally a good thing to do, but there are situations where you might not want to do that. So if I'm trying to measure something that you might start paying attention to, if I start asking you questions about it and I don't want you to pay attention to it, maybe I shouldn't be doing a pretest, right? If my study requires a little bit of deception, right? I've told you that I'm testing your reflexes, but really I'm testing something else, right? I don't want you to pay attention to that something else. And so maybe I don't do the test or evaluate you until after the fact, because I don't want to bias you with giving you the pretest. Another situation where this might not be possible is when we're dealing with something that's very temporal, right? So if I'm trying to motivate people to go out and vote, and I've got my sort of regular population that I've selected, and I've got my treatment population that's going to get a 2-minute inspirational video in which celebrities tell them how important voting is, I can assign that treatment, but I can't test, are people going to vote before that? I can ask them, do you plan to vote? But that's not the same as actually showing up at the ballot box. And people aren't going to show up at the ballot box until a particular point in time, until the election actually is happening. And so there's no way to really test that and measure that beforehand. Another thing that pops up in experimental design that people pay a lot of attention to is how much information you give to your subjects. And we've sort of hinted at that a little bit with this idea of pre-test, post-tests. But the concern is that if you give people too much information about what you're looking for, about whether they're in the treatment group or the control group, you can end up biasing your experiment. And this is something that in the medical field, people pay a lot of attention to because of the placebo effect, where simply giving people something in terms of medicine will convince them that they're feeling better, they'll report better health or less pain or whatever it is. And they do that just because they believe they're receiving medicine, and that's what should be happening. And so you don't want those, you don't want a situation where you are attributing a positive effect to a drug, but it's really just a placebo. And so the way that you can control for that is to essentially create a situation where whether you're in the treatment group or the control group, you don't know. And you're going in for regular checkups at the exact same frequency, whether you're in the treatment group or the control group. The treatment group gets a pill that's red and the control group gets a pill that's red, and they're completely indistinguishable except that one is actually sugar inside and the other one's medicine. You don't want to reveal information about what other people are reporting for symptoms, right? So if people are coming in and I'm saying, oh, are you having headaches? A lot of people are reporting headaches. Suddenly your brain's going to key in on that and say, oh, headaches are something that I should be experiencing, or I should be noting. And suddenly things that you wouldn't have reported before that are headaches or headache-like start getting reported because I've been sort of prompted to pay attention to that as something that is likely to result from being a part of the experiment. So one way that researchers often try to get around this is by creating what are called double-blind experiments. And that means that the subjects don't know if they are in the treatment group or the control group, but the researchers also don't know if the subjects are in the treatment group or the control group. I imagine somebody somewhere knows, but certainly not the person who's interacting with the subject, not the person handing them the red pill. They don't know if it's a sugar pill or the medicine. And the reason for that is that you don't want that interaction to potentially look different if I think you're in the treatment group and I think you should be feeling better, or I interact with you differently because of you're confirming my expectations about what should be happening in this study, and therefore I'm giving you that positive feedback. If I don't know whether you're confirming my expectations, if I don't know if you're in the treatment group or the control group, I can't subtly, through body language and facial expressions and tone of voice, cue you in that you're giving me the information that I want. So a double-blind study can help to control for a lot of these sort of subtle ways in which our own behavior can make treatment groups and control groups different. Okay, so I want to talk a little bit about this idea of experimental validity, or validity in the context of experiments. And validity is something we're going to talk a lot about, but in this context, validity really just means how do we know that this is true, right? How do we know that the patterns that we're seeing, the difference between the control group and the treatment group, that that's a real pattern that we've established non-spuriousness, that we can make that causal claim. And experiments, true experiments where we actually control randomization and are able to control the setting, are really good on internal validity. In fact, we don't have a stronger kind of research design than a double-blind randomized controlled study. Comparative studies, which we'll talk about later, and statistical analyses, they tend to be weaker when it comes to internal validity in terms of structuring the design in a way that helps us to make those claims about causality, because we're sort of limited by, have I thought of everything? Have I worked through all of the possible other factors that could be driving this pattern or could be accounting for this relationship? And with a true experiment where I have randomized control, I don't have to stress about that because the groups are comparable in every possible way. And so it's unlikely that any difference between groups is going to be accounting for differences that I'm seeing. So that's certainly a limitation of maybe statistical techniques and a reason to sort of celebrate the experimental method. However, experiments are oftentimes, not always, but oftentimes very weak when it comes to external validity, which is I've identified this relationship, but do I know that this relationship actually works out in the real world? Because I've identified it in a fairly artificial kind of situation, right, where I've assigned people to these treatment groups and these control groups, and I'm monitoring them and measuring them regularly, and it's in an artificial kind of laboratory setting. It doesn't look like how people live their lives normally. And so do I really know if this is something that will play out? And I could point this out in two ways. One of the most overstudied populations in the entire world is college undergraduates, particularly college undergraduates who've signed up for Psych 101 courses and get sort of routed into psychology experiments. We know lots about college undergrads, but there are things that make college undergrads different than the general population, right? So age is one obvious difference, that we tend to have a younger group of people. The life experience of college undergrads, what they're experiencing is noticeably different than the general population. People are surrounded by a much larger density of people kind of their own age, whereas in sort of the larger world, you're interacting with folks who are of a wide variety of ages. So there's lots of things that would make an undergraduate population different that maybe suggest that if I find a relationship or a pattern or something that works with an undergraduate population, I don't know for sure if that's going to scale up. If that's a function of this is how undergrads are, or they have a particular background or mindset or set of experiences, is that going to play out in a larger context? I just don't always know. And that's because experimental designs are oftentimes weak in terms of external validity. I'll give you another example of why experiments are potentially not perfect. And that has to do with how we screen folks for who gets to be a participant in a study. And particularly medical studies will screen participants coming in because they don't want people who are dying of cancer if this is a study on something that's not cancer. And so as a result, you fill out a form before you get brought into a medical study where they'll ask you, do you have chronic health conditions? Are you taking any medications regularly? Are there any things that we should know about your health? And they'll screen out people who don't fit a certain profile of generally healthy folks that they want to compare. Now they're going to put those generally healthy folks into two randomly controlled or two random groups so that they're identical in terms of the groups, the comparison group, the control group, and the treatment group. But that pool of people isn't necessarily reflective of the larger population. Historically, women were screened out of medical studies, that doctors only studied men and the effect of medications on men. For decades, women were just simply screened out as not a relevant population to consider for study of how medicines work. But because we're screening out these other factors, we actually don't know about how some of these medications that work really well in clinical controlled studies will affect people living their everyday lives. And so one of the places where we see this is with medicine interactions, that if I'm taking one medicine and I add in a second medicine, are those two medicines going to interact in a way that makes me feel sick or magnifies my symptoms or cancels each other out, or how do those medicines work together? And we really have very little information on that. It's pretty rare to see experimental studies where they are looking for medicine interactions. A lot of what we know about medicine interactions is kind of anecdotal. Doctor prescribes a new medication, you take it, you come in and you say, hey, doc, I'm feeling really dizzy. What's going on? And they say, oh, well, maybe there's a medicine interaction. I'll make a note in your chart and we'll try something else for you. And collectively, those sort of notes and charts get aggregated up to say, oh, wow, it seems like these two medicines don't work particularly well together. But that's a much less systematic and much less rigorous kind of process than what we sort of get promised with experimental design. And it all sort of boils down to the same problem of experimental designs tend to lack external validity. We don't know how things will work in the real world. I should give a caveat, unless we do a field test, which is where you go and check to see how this works in the real world and monitor and look for, are things playing out as we expect. Another place where this can actually work is with what are called experimental surveys. So typically we don't get our pool of research subjects for experiments through a random process selecting from the population. Our pool of who opts into experiments tends to look different than the general population, but that's not a requirement. That's just a practicality of how we oftentimes run studies. If we're doing something that's maybe more informational, it might be possible to merge an experiment with the way we typically run random surveys where we call people up and ask them questions. And so this is a method or a technique called an experimental survey, where you build an experiment into that process of asking people questions through a normal survey. And this gets used quite a bit in marketing. This gets used quite a bit in sort of election campaigning, where messages will get tested through experimental surveys, right? So you call up a random population, right? 1,000 people drawn at random, that's going to look more or less like the population that you're interested in. We'll talk a lot more about sampling and how that all works, but for now, we'll just sort of go with drawing a random sample, give you a more representative picture of the population. You break that random sample into 2 or 3 or 4 groups, and you give them different information. So maybe in the first group, I'm not going to give them any additional information. I'm just going to ask them, how likely are you to vote for this particular candidate? Now I've got my answer, I've got my control group. But for other folks, I'm going to ask them that question after giving them a particular message. So as you may know, there's an election coming up. And did you know that so-and-so owns a bunch of properties that have had health and safety violations, and critics charge so-and-so as a slumlord? Oh, I did not know that, you say. And then that you're asked the question, how likely are you to vote for so-and-so? And you give your response. And they take that and they note that down. And I think, does accusing this particular person of being a slumlord reduce the likelihood that people will vote for that person compared to the control group where we didn't tell them that? We could test a third message, right? Did you know so-and-so kicked puppies, right? Oh, I did not know that. But now that I do, I'm going to answer that question. How likely am I to vote for that individual with much less likelihood of voting, right? So experimental surveys allow us to kind of merge those two ideas of a survey where you ask people questions together, along with providing different randomly selected subsets of that survey, different information to see if it elicits a different response. And again, that works really well when we're interested in things like messaging. It doesn't work so well when we're interested in things like behavior, because saying, yes, I'm likely to vote in a survey is not necessarily a reliable indicator of whether a person will actually go and vote. And so experimental surveys work great for information and attitudes, and less well for studying behavior.